So what happened before the Big Bang? This is the Space Cafe podcast, and I'm Marcus. The space industry is blooming and booming. So I guess this is why you're here, because you want to be at the pulse of history in the making, perhaps. Yet there is one thing that has been troubling me for a very, very long time. No matter what we currently do in the space industry, how much time and money we invest, how many ideas and visions we have, the size and shape of settlements on the moon, on Mars, faster propulsion technologies to get us to the next and remotest corners of our celestial neighborhood, the baby steps we're making towards becoming something like an interplanetary species. No matter what we currently do, we still cannot ignore our greatest embarrassment of them all, the sheer lack of an answer as to what all this is out there. This vast void of omnipresent existence that seems to have ever been and may ever be. Considering such dimensions, we're not even a speck suspended in a beam of light, not even a grain of sand in a myriad of sand grains. We're but a thought in a timeless universe. And still, hubris alert, we may be the only ones. Yet statistics and the Drake equation speak against us. So what is all of this out there? What are our best guesses at the moment? No observation, no machine, no current technology can yield an answer. So our best guess is to go back to what makes us truly human, to go back to the naked and unobstructed power of the mind, imagination. So I sat down with the head of theoretical physics at CERN, the world's most renowned particle physics platform, hoping to find answers. Gian Giudice attracted my attention with a recent publication, What Happened Before the Big Bang. I knew I couldn't leave this place without this interview. Ladies and gentlemen, please welcome the head of theoretical physics at CERN, Gian Giudice, to the Space Cafe podcast.
There is, when you do theoretical physics, there are no limits, and speculation, imagination, hypothesis is our bread and butter. I mean, we like that, we enjoy that, so certainly there's no difficulty. The difficulty is finding reliable theories and having ideas about the origin of the universe.
Shall we backtrack a little and let's find out where physics is at the moment when it comes to understanding the origins of everything, the Big Bang. What do we know and how do we know it and why do we know it?
So it is really amazing how far we went in the understanding of the origin of the universe and how much we went back in time. It's really fascinating that humanity, from a little corner, both in space and in time of this universe, was able to reconstruct its structure and reconstruct its history. But I think it's fascinating not only that we can comprehend the universe, but also that the universe is comprehensible. It means that there are some universal physical laws that govern the universe in its entirety. And now, in this aspect, one may say, okay, but what is the role of human life inside this structure? And this brings it to a very puzzling issue, which is at the basis of what we're trying to do with cosmology. You see, because when one studies cosmology, realizes that the equations that rule the large-scale behavior of the universe allow for many possible solutions. A large variety of solutions. Nevertheless, in almost all of these solutions, life will not be possible. And when I'm saying life will not be possible, I'm not talking about some very specific biochemical process that has forbidden our form of life. I'm just saying about the essential features of the universe. Most of the possible universes that we can mathematically find simply either do not live for long enough, they would collapse before, or they would simply expand so fast that nothing could be left. So what we are finding is that our universe is extremely unique, is extremely special. And this is the big question for me about the Big Bang. Understanding how is it possible that the universe has developed exactly those conditions such that we can be here and wonder about those conditions.
This is so fascinating. It almost sounds like it's a coincidence that the universe developed in this way, because we know that there has been almost a symmetry between matter and antimatter, but though almost, and this imbalance maybe was the reason, an error was the reason for us to exist. Can you go as far as that?
Yes, that's one example, but there are lots of this kind of examples. They show that our universe has very fragile features, and yet those features are really essential. You are talking about coincidences, and it's absolutely true. Superficially, you look at that and says, well, this is just a coincidence. Why the geometry of our universe is just so perfectly flat? And many questions like that. And this is a role of science. When you see a coincidence, the first thing that a scientist would wonder is that really a coincidence? In a sense, it's like Sherlock Holmes, right? When Sherlock Holmes finds a coincidence, the dogs that didn't bark. I don't know if you remember that story. You may just accept it as a coincidence, or if you have a more scientific attitude, you wonder, is there an explanation for that? And this is the basis of understanding what's before the Big Bang. Since what we understand now is that we understand fairly well the history of the universe up to the Big Bang. We can trace it back. We can identify with very high accuracy when the Big Bang happened, 13.8 billion years ago. And we can understand quite well what must have been the conditions of the universe at that instant, simply by tracing back with our equations what we observe today back in time. Okay, one may say, okay, boom, you have now you know everything about the universe. But a scientist, when goes back and finds out that those initial conditions are very peculiar, naturally they wonder, why is that so? And this, in order to address that question, the only way is to assume there must have been something before the Big Bang. And today we have a lot of evidence for what happened. And when I'm saying evidence, I'm not referring only to logical deduction, because of course this extrapolation is based on logical deduction of the known physical laws. But, and this is the amazing part of the story, we also have a lot of observational evidence that support the story of what happened before the Big Bang.
Well, things are getting really interesting. I'm in extreme awe of those questions because these are the very, very big questions we're discussing here. So before we talk about what happened before the Big Bang, can you walk us through now and the time at the Big Bang, those 3.8 billion years. 13.8 billion years. So what happened in between? If we make a speed race through time.
Yes. So the history of the universe is as a period which are relatively quiet of evolution. Of course, the space expands. As space expands, temperature decreases. And so the universe then sort of coasts in this situation in which things modify. And then from time to time, there are drastic changes, what we call them phase transition. I mean, really a change either in the structure of space-time or in the properties of matter. And there are many of these events, and those events are really crucial for the history of the universe, because all of a sudden the properties of matter, of space, change abruptly. In this perspective, what has been understood that also the Big Bang is such a sudden transition. It's a sudden transition, therefore it's not that nothing existed before and then all of a sudden. I remember, you've probably seen some of the TV sitcom, the Big Bang Theory, right? Yeah. You remember there is a song in the beginning. I won't sing it, but I can tell you that the words. The song starts by saying, "Our whole universe was in a hot, dense state. Then, nearly 14 billion years ago, expansion started." It goes very well with the music. But believe it or not, it's not scientifically accurate, this statement. It's not that there was nothing and then all of a sudden space started to expand. What we understand now is actually before the Big Bang, before this fatal instant 13.8 billion years ago, space existed, but it was completely empty. There is no matter around. There is, the space is empty and dark, but there must have been around some place, at least, where there was some vacuum energy. Now, vacuum energy is a very strange form of energy, which is not very familiar to us, but has this effect of exerting a repulsive gravity. We are used to think of gravity as something that attracts. Instead, there is a possibility, this is in the context of Einstein theory, that space, this vacuum energy forces space to expand suddenly. So what we believe is that there was a phase before the Big Bang in which it was nothing other than this form of energy. And space is expanded at a frantic rate. And then at a certain instant, this energy converted, exactly in a phase transition, converted into thermal energy. That's the instant where matter started. That's when matter took life. And so the universe, in the sense of what we mean universe, I mean existence of matter and so on, really started there. But this does not mean that space started there. This is, the Big Bang is associated with this picture that maybe in the 60s and the 70s made sense of this big explosion. But we know by the data that there was no explosion, because if you had an explosion, it means that there is a center, a point where this thing started. And then we would be able to identify in the sky either where is the center or see the shock wave that came out of the explosion. On the contrary, if we do, when we do astronomical measurement, we see that the universe is extremely uniform. There is nothing that hints towards an explosion, nothing that hints towards the starting of that. So the Big Bang was not an explosion of a point, but rather a phase transition that happened at a specific time, but not at a specific point. It's a uniform transition that modified the properties of space-time. And during this transformation, the energy which was hidden in the fabric of space-time, so it would be completely invisible if you want to observe it, all of a sudden becomes the matter that we observe. So this is the explanation that we have today. One may think, okay, it's a nice story, but how do you know that it really happened that way? And there are two ways of understanding. First of all, the important thing is that this is not simply a story, but it's really a scientific theory. And out of that, you can compute precisely the properties of the universe that emerge from this transition. And surprise, surprise, if something like that happened, the possible universe that emerged from this transition has very specific properties. It's not possible to create a generic universe. No, has to be a universe with extremely precise property. Well, it happens that those properties are exactly those that seem mysterious just from observation. So really, this turns around completely the story, because as I was saying before, is that we are puzzled by the initial condition of the universe, by these properties, because they seem coincidence, a miracle. You may say, well, maybe there was some miracle at the beginning, some divine entity just chose those properties because they wanted to create us, because it really looks that those properties are chosen to allow for life. And then what we find now is a scientific theory that dictates some properties, and lucky for us, those properties are exactly those compatible with life. So this is first a very strong indication that we get, but there is even a more quantitative indication that comes from the following amazing, for me, consideration. So as I was saying, in this pre-Big Bang phase, what happens is that space is empty, there is nothing, and expands like crazy. So dilutes everything in all possible ways. And this is the process that makes everything homogeneous at an incredible level. Because it's, it's like if you take a sheet and then you start pulling it like mad, at the end, no matter how you started, this is perfectly flat, perfectly. And this is what happened in the universe. So this process is sort of erases any information from the universe of what the state was before, and necessarily ends up with only one possible configuration. And this is a configuration we observe.
Was this now an expansion of, it wasn't an expansion of space, it was an expansion of energy?
No, it's an expansion of space.
Because you mentioned that space has been around already.
Yes.
And it was just empty.
Right. Empty, but at a certain point, at a certain instant, we don't know when, we don't know how it started, but this empty space, when I said empty now, it's a matter maybe of terminology. Empty in the sense there was no matter. There was dark, it was cold, but inside the fabric of space-time, there is a form of energy. So there is something, if you wish, there is some form of energy, but this form of energy is not associated with some kind of body, some kind of matter, as we always think, right? I mean, the energy, we associate something that carries the energy. In this case, instead, this energy is really carried by the structure of space. And this pushes the space into an amazing expansion. So you may say, well, how do you measure it? Because there's nothing in it. But you can mathematically define distances, and you find that these distances have an exponential increase. Now your question, if I understand it correctly, you may say, okay, but then if you have a certain energy inside and then you dilute a space, you also diluting the energy. No.
So it's the opposite.
The energy density, so the amount of energy per volume, remains constant. The amazing thing, and I we can discuss why. What happens in this universe is that the energy density remains constant, and yet energy is conserved. It's like take a city, for instance, right? I mean, it's a very quickly expanding city. Let's take Beijing, one example, right? I mean, every time I go to Beijing, I find that they have the ring roads. Well, every time I go, I don't go frequently. There are more rings. The city has expanded. So the city has expanded, and when they have buildings everywhere, so pretty much with a good approximation, the population density remains the same. That means in every kilometer square, there is the same number of apartments, same number of people. But yet, Beijing expands. Of course, you say, well, because the population is growing, more and more people from the countryside go to the city, and that's what creates this large increase. So you think that necessarily you have to feed something, in that case, inhabitants to the city. Well, the amazing thing about this process of expansion, which is called inflation, is that in spite of space increasing at an amazing rate, the energy density remains there. And yet, there's no creation of energy. The secret is, again, a conversion of energy. So the energy was hidden in a form of gravitational energy, and then it converts into the energy of space. And this is what drives this amazing process.
And it never gets lost.
It never gets lost until one special moment, which happened 13.8 billion years ago, in which all this energy is not lost, but changes form. This energy is completely transformed, converted into thermal energy. It means the movement of particles. But as I was saying, this process then makes the universe perfectly uniform, and then you can say, okay, fantastic. You have a story now of how the universe started, but you're just telling me that necessarily the universe must be uniform to an amazing degree. And so in first approximation, say, well, it's good, because actually, we certainly don't observe uniformity around us. But if you make astronomical observation at very large distances, you find that the universe is roughly uniform.
What does that mean? Is it spherical?
So I'm just saying locally, the general shape of the universe is not known. What is known is the local geometry. Now there is a difference. Let me explain. So suppose that you are a bidimensional creature that lives on the surface of the Earth. Okay, which pretty much, we're not bidimensional, but we move along there. And nothing else exists. Okay, space doesn't exist, or what's underneath the Earth doesn't exist. Yet the meaning that your space is curved is something that you can measure, because you can make experiments that tell you if your space has some intrinsic property, which we call curvature, which tell you that the geometry of space is something different. And what is possible is to measure the local geometry of the universe. It means local, within the range of the universe that we can directly detect. And what we have observed is that, at least as far as our instruments go, that the space is not only uniform, but extremely flat. So there's no curvature. The space just follows exactly the rules of Euclidean geometry, what we study at school. Okay, so everything is very smooth and which is a puzzle, as I was saying, and then finds explanation in this process. Now, this is a fantastic solution, but it comes with a problem, with a puzzle, because you may say, okay, good. Now you have explained why when I observe the universe, is approximately flat. Then you can say, good, but you're telling me that this process is so efficient that everything should be perfectly homogeneous. And yet we know that it's not, okay? I mean, we have on Earth, we have the sun outside, there's a planetary system, there are galaxies all around. So how is it possible? Again, you may say, well, it's something magic, but we are doing science. And this is indeed a good scientific question, because we know that gravity, since it makes matter collapse, can increase dishomogeneity. So if you start in a system which is a little bit dishomogeneous, you wait long enough, you know that matter will try to clump. So that is why we observe a unit. However, in order to do so, you will need to have some initial dishomogeneity. If you have a perfect homogeneity, well, you'll never create any, because gravity cannot, because it doesn't know where it is. And this is a puzzle, and the resolution is just magical for me. And the resolution is that when you think about this process of space expansion, you should not forget about quantum mechanics. Now, quantum mechanics is the theory of the microscopic world. So it's a theory that is relevant only at very, very short distances. For instance, we don't usually feel quantum mechanics simply because it's not that quantum mechanics does not exist in our real world, but our resolution of space is not sufficient to start seeing this quantum. Now, you may say, well, if I don't see quantum mechanics at our distances, let alone the whole universe. But here comes a difference, and the difference is exactly this process of inflationary expansion. Because the expansion is so fast that even something that happens in the microscopic world can start affecting large distances. So what is understood now is that if you start from a situation in which the vacuum energy is perfectly uniform, but you take into account quantum mechanics. Now, quantum mechanics, what does it do? Quantum mechanics tells you that physical reality is never perfectly determined. This is the Heisenberg principle. The Heisenberg principle sort of incarnates the essence of quantum mechanics, tells you that the world is not perfectly predictable, that there are some intrinsic uncertainties that do not depend on the precision in which you measure things, but they're really part of nature. And these uncertainties are absolutely real, which means that even this vacuum energy must have felt some kind of uncertainty, some kind of fluctuations. When these fluctuations are microscopic, so you may say are irrelevant, but then this enormous expansion brings this really tiny fluctuation to distances which can be enormous. So what happens is an interplay between quantum mechanics that keeps on creating uncertainty at small distances and space expansion that stretches them to astronomical distances, to distances larger than the whole physical universe. And now physicists can do precise calculations of this. This is not just words. You can really calculate what should be the celestial structures if indeed the universe was in such a state. Well, the amazing thing is that these calculations have a remarkable comparison with the direct observation, both of the distribution of galaxies, but also of the anisotropies, which means the small variations in the temperature of the cosmic microwave background. The cosmic microwave background is an electromagnetic radiation that fills the universe, which is known to be very, very uniform. Nevertheless, some modern experiments have shown that its temperature is not exactly uniform, but there are variations at the level of 10 to the minus 5. So 1 part in 100,000 has a tiny, tiny variation in its temperature. And this tiny variation has been measured very carefully at all distances. And then theoretical physicists compute what should be these variations if there was some pre-Big Bang phase, and smack, the two things match perfectly. So it really, for me, it's an amazing story. The story is that when you look at the sky and you, not by eyes, but let's say with telescope, you start seeing all galaxies all around. Well, those galaxies, the pattern that those galaxies form is not like a constellation telling about ancient heroes, but they're telling you about the quantum fluctuations that occurred in the vacuum energy that existed before the Big Bang. So there is an amazing connection between the microscopic world, the physics of the large distances, and the history of the universe. It's one instant in which when you realize this, you just look at it and you think of the beauty of the universe in the sense of the harmony that exists among the various theories, the various physical laws that describe the universe at any possible distances, and they cooperate in order to create something which, amazingly, is so very special and is one of the few possibilities that allow for a universe to live long enough and therefore to generate stars that can ignite and then that can produce a life.
This is incredible, and it sounds very uplifting that we are on the right track. Science is on the right track in order to help us understand ourselves, the origin of matter, of energy. But still, it's just 4% of everything we understand. And this is, at the same time, it's frustrating, I could also imagine. So everything that you just mentioned is 4%. Is that right? And,
yes.
And how about the rest?
Right. The rest is largely dark energy. And then there is a good fraction of a quarter of dark matter. Now, the dark energy is probably the most interesting aspect. And the reason is that, we understand fairly well what dark energy is because it's exactly that kind of vacuum energy that I was talking about. So it's amazing what we see today, that the universe is largely filled by some kind of energy which we think was the same energy, same form of energy, not the same nature, but the same form of energy that started the whole thing. And yet, we have this puzzle, and the puzzle comes when we say, okay, we understand what this is. Can you tell me what is it made of? What is the stuff that makes this dark energy? And at the moment, unfortunately, we have no clue. Actually, for particle physicists, the puzzle is not why there is dark energy, but on the contrary, why there is so little dark energy. Because according to particle physics, the existence of vacuum energy is something that should be there. And it's based on quantum mechanics, pretty much. And therefore, we would have, if you ask any physicist, you describe the universe, even if, some alien that's never been in this universe. And you just given the properties, say, okay, compute and tell me what's going to be in this universe. And, they make some estimate and they tell you, well, it's all dark energy. And instead, it's not. Luckily for us, that we can exist without. And so the puzzle is to understand why there is so little and what is it made of. And at the moment, we do not have a good explanation. And this is probably the one of the biggest puzzles that we're encountering. Not the only one. You mentioned dark matter. Dark matter is another issue in the sense that what we observe is that there must be some other form of matter that exist in the universe. In that case, we have many ideas in the sense that many of the current hypotheses in particle physics predict new forms of matter. And therefore, it's not so strange that this dark matter should exist. On the other hand, we still don't know what it is. We don't know its nature.
Does all this require a profound paradigm shift in our understanding, or would it just need an additional add-on, like the understanding of the Higgs boson? Because this is not, it's a major discovery, but it's not the paradigm shift that may be needed in order to understand the 96%.
Yes, I agree with you. It would be a major discovery. Okay, obviously, understanding. Is it a paradigm shift? Yes or no? We don't even know how to answer that. In the sense that it could not be a paradigm shift. It could be that it's just saying is a modification of our understanding of the particle physics. We have missed some part of the story, and that part takes into account for this matter. There are many, many examples. There are many particle physics models and theories which indeed have this additional element, and this additional element matches what we observe.
But could it be that at some point we're waking up because someone has a brilliant idea, and we're waking up and we're realizing that the standard model is completely wrong, that quantum mechanics, that relativity, that everything is wrong? Is there a possibility that something like this happens?
That's a dream for a theoretical physicist. Maybe a nightmare for an experimentalist, but it would be a dream. I mean, I think that the big paradigm shifts are the moments which are the best moment to live for a theoretical physicist. This is when I read book of history of physics, and I think the moment in which quantum mechanics was invented. I mean, it's something really magical, and you see everything you know crumble around you. I mean, this at the time of quantum mechanics, I would say it was like relativity was fundamental, but it is there is a logical path that led from Newtonian gravity to a new vision. It was a fantastic step. But yeah, there is a continuum. Quantum mechanics was really a collapse of a whole conception of the world, and the birth of a completely different one, which probably we still do not fully understand, because there are many, even if quantum mechanics is tested at an amazing level, and also it's a theory in which we can calculate things, processes, probabilities. We can do it with an extreme accuracy, and as this has been tested, so there's no doubt that the framework is correct. Yet, when we stop and think of what is the meaning of this, we are puzzled. In other theory, like saying, for instance, general relativity is a fascinating new vision of what the space and times are. But you can visualize it. You do understand what it is. In the case of quantum mechanics, when you get into these deeper problems of what is the meaning of reality, then you are confronted with puzzles that, unfortunately, our current theory do not reply. Now, maybe this is just only a conceptual obstacle because, again, from the practical point of view, we can go. However, it becomes more practical when you go in regimes where quantum mechanics and general relativity come together. We understand very well both theories. However, when both theories when the facts of both theories become really important, we are losing track of what happens. Essentially, it's very easy to understand why. I mean, quantum mechanics is telling you that physical reality is not a continuous medium. it breaks down into some components, what we call quanta, right? Quantum mechanics is from that. Some individual elements that compose reality. And we have understood that in the case of matter. Matter is not a continuous mean, but is formed. At each level that we're going down, we discover new layers, right? You go from molecules to atoms, to nuclei, to protons, to quarks, and so on. So there are many layers, but that we see that, and then there's no continuity. There are some individuals. General relativity told us the big lesson was that space and time are not some external entity to physical reality. I mean, we are used to the vision of Newton, but also the vision of the physics that we study in high school is that space and time is a stage where physics happen, and the physics is the motion, are phenomena that involve matter. What Einstein told us is that this picture is wrong. You cannot separate the two things. Space and times are not external, rigid entities, but they're part of the physical reality, and they interact with matter. They modify, they change, the space and time is deformed, is contorted because of matter, and at the same time affects matter. So they're part of it. Okay, then if quantum mechanics told us that matter is made of individual quanta, and relativity tells us that there's no really fundamental difference between matter and space and time, when the two theories come together, you have to understand the logical conclusion is that, well, also space and time is not a continuous medium, but is made by some entity, some quanta of space and time. And the big question is, what are these quanta? What are these elements, these fundamental elements that make up space and time? Well, we don't have an answer to that. And this is another of the big questions that we are facing. And this is not simply just an academic question for theoretical physicists, because when we get to certain systems, this is very important. And one of the cases is the early universe, because in the early universe, there are conditions in which gravity is important, of course, because gravity really determines the behavior of full properties of space-time. And on the other hand, quantum mechanics, as we were saying, play a critical role in determining the properties. So the two things cannot be separated. And when they come together, our description fails. And this is the big limitation today to proceed in our voyage towards the origin of the universe.
You mentioned something critical when you mentioned that maybe we haven't caught up with an understanding of quantum physics in our everyday lives. We build computers with it. Through its understanding, we build the world based on the understanding of its implications, but still in our everyday view of the world, we haven't integrated that in our minds. So my question to you, maybe it's a personal question, how do you as a theoretical physicist see the world? Do you see a relativistic world? Do you see a quantum state world? Or are you still in a Newtonian world? Because as like space around us seems to be rigid, seems to be following Euclidean geometries. Because what I'm trying to get at is, at school, in our educational system, we're still learning a Newtonian vision of the world in popular culture. So the relativistic culture has not caught up even more than 100 years now. It's not part of my view of a world. How's that for you?
This is absolutely true. And I think it goes even beyond what we are taught in school. is that, Newtonian physics, classical physics, is part of our perception. I mean, it codifies into equation our perception. It's, you'll understand the mathematics, differential equation, blah, blah, but at the end, once you have understood, it really corresponds to what you feel about reality. Well, quantum mechanics and relativity, no. They are telling you about a reality which is really far from our perception. Am I able to think in those terms? Personally not. I wish I could, but personally not. And I have the impression that maybe there are exceptions, but every physicist the bottom thinks in terms of classical physics. We are trying to always, when we solve a problem, to construct in our mind some picture, some modeling, which corresponds to some process of classical physics. I mean, when you talk about, protons colliding, everybody thinks about the little balls that come together and bounce. We know that vision is completely wrong, okay? Particles are not balls. Particles do not bounce against each other and they're reflected. And yet, when we develop our theories, we have that picture in mind. I think it's our brain is hardwired with evolution since we came out of caves and even before, which is based on what we feel. So it is very, very difficult to construct. The trick of physicists is somehow to try to understand the phenomena in the language of quantum mechanics and relativity, and then form a picture in the mind that helps you to navigate into this new world. But eventually, the real way of navigating is trying to forget about intuition, because intuition will tell you the wrong thing, but use mathematics. Mathematics is really the medicine for all this, is the trick, because mathematics is not going to cheat you. And if you, for instance, you were giving the example of curved geometry, it is very difficult to visualize curved geometry. Okay, we can do it maybe in 2 dimensions because you can think of surface, or I can throw you some pictures, you get an idea. But here we're talking about curved 4 dimension of space and time. Well, forget about even visualizing 4 dimensions, which we cannot. But when we're saying visualizing a curve, it's just completely impossible. Nevertheless, these steps of going from 2, 3, 4, n dimensions in mathematics is completely trivial. It's very simple. And then we use mathematics, we solve the equation in that dimension, and then we discover some phenomena that maybe do not exist in 2, 3 dimensions, but they exist in other dimensions, and then we use them. So really, at the end, of course, you need models in your mind in order to navigate, to process. But what you have to trust is mathematics. The language of mathematics is much more powerful than the human brain, in a sense, because it doesn't require you to construct a model to try to understand what's going to happen, but it's going to give you the answer. If you have in your hand the right equations, you have to continue and find a solution. This is, in a sense, was one of the biggest mistake that Einstein, a genius like Einstein, did. That he looked at his equations, and they found out that if you trivially solve them, you find that the universe expands. And he thought it was so stupid, so unreal, that this cannot be true. And so he modifies the equation, trying to look for it, because obviously the universe is not expanded. The universe must be eternal. I don't know what does it mean that the universe is not eternal. And so, or another example is Dirac. Dirac, another genius of physics, solved and found the equation that was describing a situation in which quantum mechanics applies to a world of special relativity. So not the relativity with gravity, but just the first version of relativity. And he found out that matter has to have a sort of a second phase. And he thought, this is stupid. I mean, this is not the case. And he worked for years in order to try to remove that from his equation. And he couldn't succeed. Mathematics was stronger than him. And then at the end, he surrendered and he said, okay, boom, this must be true. And so there should be an antimatter. Well, antimatter was discovered. As he said after, he said, my equation was smarter than me.
Fantastic. In a different universe, could mathematics be completely wrong, the way we understand mathematics?
This is a very deep question. The question is mathematics you're right. I mean, is a human construction, or is it just that it belongs to nature? Yeah. And if you ask different physicists, you're going to get very different answer. My personal answer, but it's not sort of based on feeling, not, of course, I could never prove it, is that mathematics is hardwired in the universe. It's not a human invention, but we discover mathematics. We don't invent it. We discover the structures, but the structures are part of nature. And this is because more and more we've seen as we continue this path of explorations is that even very, very abstract forms of mathematics that we invented, then we find them in nature. Curved spaces, non-Euclidean geometries are a perfect example.
So it's like they say that Michelangelo said that he's not crafting those sculptures, he's just freeing them from the marble around. So maybe this is also something that the marble quarry is around, and our goal is, and our task as humans is to get rid of the marble, to free it, to make and lay the structures free that are already built into it.
I like very much this image that you're giving, and I've never heard before that Michelangelo said that, but I think it applies to at least my vision of mathematics very, very, very much. Mathematics is something that exists in the universe. It is, to me, probably the biggest discovery of science, the discovery of physical laws. The very fact that in nature there are physical laws, there are some repetitions, and which govern the way the nature changes, is just a remarkable fact. One could argue, one could think of, is it possible to have a universe without physical laws? Could we have a universe in which, the physical laws are just accidents of various parts of reality? We don't know the answer, but probably not. I mean, really, in order to have reality, you need to have some logical structure behind it, and this is what we are finding. And this logical structure has a beauty and a depth which is just astounding, and indeed uses the most complicated structure, at least for our brain, most complicated structures of mathematics to express then something which is extremely simple. And that's the beauty of it. Take general relativity. I mean, general relativity, and when you study the mathematical, differential geometry that is required to understand, it's extremely complicated. It's not something that you can study in high school. And yet, when you get to the bottom of the theory, you understand that the theory is based on an extremely simple principle that can be essentially, stated in one equation or one line, and then out of that, all this structure. So it really seems that nature goes for an intrinsic simplicity. But in order to express that simplicity, it doesn't mean it uses a language or a structure which is non-trivial. And this is the secret of life, in a sense that, it's very pleasing that that nature follows simple principles. But then you may say, okay, start with simple principle and then make a construction. I can give you some Lego pieces, right? I mean, very simple. And then you combine them. You can make a construction. The construction can be big, but you're not going to be able to create life, okay? And why? Because if I give you some simple elements, you're going to have a simple construction. The beauty of nature is that starts from very simple basic elements, but those basic elements are secretly rich enough that when you put them together, you create something which is completely different than the original element, and something that can be so complex as life. Of course, one may say, okay, now what's before that? You're telling me that space was empty, yet had some vacuum energy in it.
But space was around already.
Space was around already. So you may ask,
where does space come from?
Space had started? Or how did this vacuum energy come about? And all these questions. And that brings us to another step of speculation. And here we are jumping. I describe also in the book possible hypotheses, but I must say straight away that all these hypotheses going into a realm in which we have no indication from data. So there are speculative ideas, some more attractive, some not, that are trying to make some connection with observation, but at the moment it's impossible. And this is lacking direct observational evidence is very complicated for us to tell which idea is right, which is wrong. What we are doing is we're using the deductive method of science, Sherlock Holmes. You get some hints from the physics, and you try to extrapolate and imagine then what could have happened and who committed the murder. In this case, who created the universe, right? And there are the ideas which are very, very different. In some versions of this idea, space has always existed, is eternal, but it went through various phases of expansion, contraction, and variation, and which were necessary to create then those conditions which have then started inflation. Other ideas instead, they assume that there was a beginning, there was a starting moment. However, when we talk about the moment, the initial moment in which also space was created, one, we have no idea if it's ever happened. We have no idea when, unlike the case of the Big Bang, that we can fix it very well in time. And also, it's even worse because we don't know even if the question, did the time start, has any meaning. And the reason is the following. As we were discussing before, when we get to conditions in which gravity and quantum mechanics start to be intertwined, we don't know what is a description of physical reality. Certainly, if there is an instant of an initial of time, you are in those conditions. So at that point, we cannot talk about time as a continuous variable. So we don't even know if it really makes sense to speak about initial instant. Hawking, with Hartle, for instance, developed an hypothesis that the universe has a beginning, but there is really no initial moment. In a sense that the idea that there are no borders of time, and yet time is limited. In one is, of course, it's difficult to visualize it, but the best way to visualize is to make the analogy with space. Consider again the case of the surface of the Earth. The surface of the Earth clearly is limited. It's not an infinite surface. And yet, if you now define the direction north, you can go from Geneva to Hamburg, and you say, well, you go direction north, and then you can continue. But when you get to the North Pole, the concept doesn't make sense. What is more north than the North Pole? And so time could, according to this hypothesis, behave in the same way. So you can go back in time, and yet the definition of what was before, what was the beginning of time, makes as little sense of saying what is more north than the North Pole. And yet time is limited as much as the Earth's surface is. So we're getting into many of these kind of paradoxes, and the reason is that we do not have a full control of what we call quantum gravity, I mean the behavior of gravity in a quantum regime. Probably before we can solve this issue, it will be very difficult to infer and understand what is the origin of space-time, and also especially to frame the question. Does it make sense? Can we talk about an origin or not?
You're leaving me speechless. Where does all this come from? Does it come from mathematics? You standing at your blackboard doing calculations? Or what is it? Is it intuition? Where does that understanding come from?
It's I think this is for me the beauty of physics. In the various sciences, I think physics is rather unique. You have more descriptive sciences, which means they're trying to understand a phenomenon. Like say in biology, you want to understand a certain process. Once you have understood it, you are happy, you have solved the problem. Then you have mathematics, which doesn't really care about reality, but they care about structure. They want to invent, they want to use just logical deduction, and they create their structure. Once they've created a consistent structure, they're happy, they have solved the problem. I mean, both of the sciences are extremely interesting and fascinating. But the uniqueness of physics is that physics lives between these two boundaries. On one side is really developed largely by hypotheses, so by using the rigor of mathematical deduction. And so it is something then developed on the blackboard. And then at the same time wants to describe the real world. So wants to connect with phenomena. The key is that physics doesn't want simply to describe our phenomenon, but they want to understand the essence behind that phenomenon, which is, if you wish, is the physical law. So the power of physics is to understand a phenomenon, extract the fundamental laws, and use those fundamental laws to start an exploration in direction in which maybe experiments have not reached. This is how we explore the origin of the universe. One may have the approach of saying, look, the origin of the universe, you're not going to make an experiment reproducing the universe. You're not going to be able to go back in time. So it's just not science. You're doing pseudoscience. And the answer is no, because what we do, we trust the universality of physical laws. We extract physical laws in experiment, for instance, here at CERN, in colliders, and then we use that knowledge to extrapolate it to the... So this is, for me, the beauty of physics. So physics is neither simply writing equation on the blackboard, nor doing the experiment on the lab. It's something that floats in between, and it's a mixture of the two. so much that is often very difficult to disentangle. Once you see a final result, say the discovery of the Higgs boson, where did it come? Was that theory that developed this idea, or were there experiments that actually found it? It's the whole development of particle physics is a story which is intertwined between observations and theoretical ideas, and that is the beauty of this field.
I'm wondering, I have in comparison to you, next to no understanding of the theory behind the universe, etc. Still, I have a kind of strange feeling that there's a very profound presence with the universe, an unmoved presence, because I do not see a conscious mover out there. And this has a huge force upon myself, because I feel like there is something out there. We have no understanding how it works. Where the hell does all this come from? Mm-hmm. And it still works. How can you, with a profound insight through mathematics, through physics, still live a happy life on this planet and not be deeply frustrated by not knowing what's going on?
I think really knowing science and physics does the opposite effect. It does not the effect of frustration or this effect of being useless in the universe. Now we understand all universe. What am I doing here? That I am just some atoms meaningless, produced by an explosion of a supernova that spit this dust in the around, and then I came. So it's the opposite. I think it's just you see some glimpse, because of course you don't see the whole thing, but see some glimpse about this fantastic order that stands behind. Does not give you a sense of frustration, but on the contrary, this just gives you this sense of being part of a grand scheme, which is uplifting feeling,
Yeah.
and so science, if anything, really gives a meaning to existence. Does not eliminate the meaning, but it gives you a meaning, because you can see that there is part of a scheme. I mean, the emergence of life was part of a scheme. Not in all universe was possible. That means that the universe somehow knew all this thing. And it's absolutely fascinating. And as I think scientists, as every human being, of course, develops their own idea about the meaning of reality, ask questions. But at the end, and this is the beauty of science, even your bias or ideas of how nature should go, because you start developing, do not affect the scientific result. Or let me just say, it does affect the scientific process in the sense that it blinks you towards trying to address certain questions rather than others, trying to find the answer that you wanted, because as part of the scheme that you developed. Well, the beauty of science is that at the end you can be proven wrong. And you had this ambition of giving an explanation that fit your philosophy about nature, but then at the end you have to compare your results with experiments, and if experiments tell you no, you have to accept it. So it's a lesson also in that sense, that our own way of thinking, which is very important in the way you develop theories, but at the end you have to submit to the final verdict, and you do not say the final verdict is nature that tells you the final verdict.
What's the ratio amongst theoretical physicists or physicists in general between those who have some sort of religious, metaphysical belief, faith, and the others, the agnostic ones?
I don't know how to answer because I've never done a survey in that direction. I would say, but again, it's not significant. It's not based on any study, but just is based on the anecdotal evidence of chatting with people, that the majority is agnostic or atheist. But that does not mean that physicists necessarily lack a spiritual feeling. This spiritual feeling may not be reflected in a precise religion, associating yourself with a specific religion. Nevertheless, of course, it depends, I don't know, but personally, the study of physics have not eliminated the interest in me of a spiritual meaning, and it's I would say that many physicists approach in a very individual way, which is not reflected then in a religion. But though, of course, in our everyday life, we don't ask those kind of questions. But in the free time, sometimes you try to see a picture and see a meaning behind what we study.
There's a question I keep asking my guests on the show, and of course, I would like to find your answer to this one. If now the call came and whoever, Elon Musk, Jeff Bezos, whoever, gave you a spot on one of their spaceships to go somewhere into the solar system, would you accept?
Depends on the length of the trip. I think I'd be fascinated of going into space. I think it must be an amazing experience. And I understand why people indeed, like Elon Musk and the other, are thinking about this space tourism, because there is, I think it's part of human nature, right? Icarus, who wanted to fly. It's just that have always been really, the idea of passing our limits, going beyond. When you climb a mountain, you also have that feeling, a little bit smaller, but this idea that you can get to the top, you can push your body to do something that is extreme, is very human, and it gives you a great satisfaction. And I'm sure that would be an experience that if I could, I would miss it. If you are telling me that I should embark in a trip towards Pluto and spend my entire existence there,
maybe not.
I would say that maybe I have other things higher in my priorities.
But anyways, it will be a very long journey to go anywhere, because Mars already is pretty far away. So my question to you, in order to keep you entertained on that journey, what kind of music, what one piece of music would you not want to miss? Because we have a playlist on Spotify where each of our guests contributes one of their tunes to that playlist. It's called the Playlist for the Aspiring Space Traveler. What's your contribution?
Whew. You take me off guard.
Any style.
Okay. Verdi's Requiem.
A requiem. Also, there is something uplifting.
Well, Verdi's Requiem is really push. I mean, if you listen to the first time, I don't think that you think there's a requiem, right? With the drums. It's actually an extremely live music. Yeah. And it is really amazing. I think that he thought of that for a requiem. I mean, you associate the requiem with this kind of sad music, and the requiem is Verdi, which is an extension of the one on Mozart. Already the one on Mozart was extremely revolutionary because, again, it's not the standard you think, but Verdi obviously started from there because the structure is very similar, but pushed it to another level. For me, if I would want to have some soundtrack of my trip, probably I would use that.
One last question. What we're doing here, the show is called the Space Cafe Podcast. It's a coffee place. As an Italian, you know what the coffee culture is like. And usually you go into, or sometimes you have an espresso to energize yourself. You wouldn't say espresso, you would say cafe in Italy, to energize yourself when you're tired. Now, why don't you share a cafe or an espresso for the mind with me, with the audiences? What do you think could be an energizing idea you would like to share now?
For me, these ideas about the origin of the Big Bang, maybe just because it's close to my research, and maybe because I've also spent time writing it for the public, but for me is one of the most amazing ideas ever produced by science, and for several reasons. I mean, one is because, of course, the question of the origin of the universe is such a big question, which has always been asked by humanity, that just the idea that now we can address that question using science, using the scientific method, not using, religious beliefs or philosophical assumptions, or mythical legends and so on, but is really using observations. And yet we can go back in time so much. That is part of amazing. And the second aspect, which I find that it's amazing, is that how much the understanding of that theory of the origin of the universe can only come if you put together some of the deepest and most important pillars of knowledge in physics. You could not understand the universe using only one tool. You really have to bring together the understanding of general relativity, the structure of gravity at the larger scales, quantum mechanics, theory of the small scale, particle physics, and all other sciences. You really need. So there is this merging of knowledge that is required to create this. And this, I find it absolutely amazing, and also shows the beauty of nature, but also the power of science. How science, how powerful it is in bringing together all the elements of knowledge and reconstruct such an important event as Big Bang.
Fantastic. Thank you very much for sharing such profound knowledge with me. Thank you.
Thank you very much.
Mind-bending, a truly mind-bending exploration of the universe's origins, from quantum fluctuations shaping galaxies to the mathematical harmony in the cosmos. Dr. Giudice has taken us on a journey that's awe-inspiring. It's humbling and awe-inspiring. We're not just observers, but an intrinsic part of the universe's grand story. That is truly star stuff, my friends. It's moments like these that remind us why we explore and question, pushing the boundaries of human knowledge. If this episode sparked your curiosity, why don't you consider sharing it with fellow stargazers? Perhaps think of someone who you think could find inspiration in all of this, could rejoice when listening to talks about or ideas about quantum fluctuations and the very moment before the Big Bang and whatnot. I'm truly moved by such moments. So perhaps there is someone else out there who's truly moved, besides you, of course. And your reviews would help our little corner of the podcast universe expand. So don't hesitate to leave one. Before you go, my friends, take a moment to look up at the sky or close your eyes and imagine the vast cosmos in this immense universe. Remember that you are unique and irreplaceable, a conscious part of the cosmic dance. Keep looking up, stay curious, and until next time, this is Marcus signing off from our cosmic cafe at Astra, my friends.